Okay, hello everyone. Welcome to lecture 13. This is video 1, and in this lecture we are going to talk about validation and model selection. These are two very important, rather I would like focus on validation, which is an important tool in learning, extremely useful. And until now, like we identified in some of the previous lectures, that overfitting is a problem, right? Because there is noise in the data and that's always there. And then we figured that regularization is a cure to overfitting. Now, in this video or in this lecture, we will introduce another cure that is known as validation, right? And then further, we'll build on that and we'll talk about something that's known as cross validation and how using these tools we can do model selection and in order to get like better models. So that's the focus of today's lecture. Let's move on. A quick recap of regularization. As I said, regularization combats the effect of noise because noise is always there. So basically, regularization puts a brake on our algorithm going astray, that was led astray by noise. And so instead of minimizing E in only, we minimize this augmented error, if you remember, which has a regularization parameter, lambda, here, and then it has this regularizer. So it has like two important components, and basically lambda is up to us what we want to how high or low we want to choose based on a lot of factors, of course. And then this lambda h was something that we called the regularizer, and how you choose to represent your model complexity is essentially the idea. So, for example, the basic idea of this is that noise is rough, right, and complex. And so, if we add a penalty to this noise somehow, we can smooth our function. So, we can prevent it from being rough. Some of the most popular regularizers that we looked at were the weight decay ones, and how much regularization we need was decided by or controlled by this knob lambda, which was the regularization parameter. And of course, for the regularizer, there were many other standard ones apart from the weight decay one, and it depends on the problem, of course, how we want to use it. And then finally, we tried to understand this lambda a little better, and we looked at different. This is known that different regularizers will give different results, and so is the amount of regularization. So we looked at this experiment of 5 data points where the data was overfitting, but by adding a little bit of regularization here, as you can see, lambda, a very small amount of that, really helped get better results. And so the choice of lambda is essentially a balance between overfitting and underfitting, or in other words, approximation versus generalization. So that's what's happening here. If we added too much of regularization, that means the side effects of using this cure superseded, or they were more as compared to the actual cure that they were offering or the actual benefits that they were offering. And so this led to underfitting. That means we were losing on a lot of information from the data because we were like simply ignoring certain important aspects of the data. So basically, we have to come up with that optimal lambda somehow. That could be through experiments, that could be through a more principled approach, and we'll see that one of those approaches is actually validation to come up with the right lambda. And so let's jump to what is validation. Okay, so even before like directly jumping into that, we know that like this is like a generic sort of representation of the relationship between E out and E in, right? So one of the uses of validation is to pick the best lambda in, like as I said, in a more principled approach. And what we're doing here is that we are somehow targeting this overfitting penalty that we also saw in the regularization discussion, right? And we have looked at this equation before, as I said, under the VC theory, or like according to the VC theory, this penalty is given to the hypothesis set, right? Larger the hypothesis set, you have some complexity that gets added, and so you're kind of penalizing your model in the sense that the hypothesis set is growing large, and so you are like taking care of that. In terms of regularization, we give a penalty for the hypotheses, not the hypothesis set. So that's a major difference between the two. Regardless, the relationship between E out and E in is similar. So now what happens? So there is another view of this relationship through validation. And what we do through validation is that we directly go for this approach. So what we're trying to do in simple words, or in principle, is that validation goes all out and says, let's estimate this out of sample error directly. That's what validation does. So that's the basic idea. That's the fundamental idea behind validation. Until now, what we've been doing with other approaches is that we are like focused on E in, and then we have an accompanying penalty term, and we have different ways of controlling it, and so on. But now what we are saying in validation is, why can't we directly estimate or somehow get this E out, right? And so we are, throughout this validation approach, we are after getting that E out, or at least an estimate of E out. So let's try and understand, because E out is the eventual thing that we want in any learning problem. So let's see how we can get that. Okay, so we are after getting E out. So let's look at the ideal setup, a scenario where like there's this ideal world where I can get access to everything, right? So let us assume we have this data set of size n. Okay, and then I have my model, which means my hypothesis set plus my learning algorithm that helps me pick the best hypothesis, which is G, right? And then what I do is, like, once I have this like best hypothesis, I have this random point. Again, I have access to everything. So this is this ideal setting, right? And so what I can do is I can calculate the, like, let's say the error is a function of g of x, because this is like my final hypothesis, right? And whatever y is. And so what I do is that I have the ability to compute the error for that particular hypothesis that I came up with. And if I keep doing that for different like random points and different data sets for this problem, what I'll get is that the expectation, and if I just think about only one point, right? The expectation of this error on G, right? On average, the expectation is that this is equal to E out of G, right? So the expected error on a randomly generated out of sample data point is nothing but like this E out. So we have found a way to kind of estimate E out, right? And in addition to this error, expectation of this error, will also have like some variance that's associated with this like error calculation, right? So if there is just like one data point, you can think about it that there would be a lot of variance because the outcome is random, right? So because this outcome is random, and we know that with just one data point, this can go really wild at times, right? So how about we generate more than one test point? Can we do that? Well, because this is an ideal world and I'm assuming I can do everything. So let me partition this. And so let us assume I have more than one point. So x1, x2, and so on up to xk, let's say. And this will be called a test data set. So this is called a test data set. And instead of like this one point, now I have like this whole set of points. And obviously, just like I did with that one single point, I can evaluate my E, like my error. I can calculate my error on each of these, right? So if I do that, basically for x1, I'm going to get something that's E1. I'm just like denoting them by E1, E2, and so on up to EK, right? So there will be K test errors. Now I want like the expected error on a test point, and like that should be approximated using these errors. So basically what I can do is I can calculate the average of these errors, because that will help me say something about E out, and that's what I'm after, right? So I can calculate, and this is known as E test. How about I calculate the average of all these errors that I calculated on each of these points? So the average of that will be 1 over k and summation of ek, where k is from 1 up to this big K. Okay, so this is known as the test error, and it is very appealing to use because this can be thought of as an estimate of E out. And let's see what is the expectation of this error. So if we calculate the expectation of E test, the expectation of E test would be, I'm just like substituting this here, expectation of 1 over k, summation k is from 1 to k, E sub k, right? And this is like linear, comes out, and so this is going to be 1 over k, And I think this has to have a summation still. K is from 1 to k. And this is the expectation of E of k. If these are like all independent points, so this is essentially the expected value on each of the test points. And this can be rewritten as 1 over k. And then, yeah, so this is the expectation. And so this will cancel out the k's and the k. And we will eventually get E out of g, right? Because this here, this term here is going to be the summation, first of all, of E out of G. So that would be like for K points. And so K times the E out of G. And so eventually we'll get E out of G. Now, what did we arrive at? What did we accomplish by doing all of this? Well, if you look at it, like the expected value of test error is exactly equal to the expected value of error on any one point, right? So this was just for one point, but here we calculated the average and found out that the expectation of the test was also E out of G. Okay, what about the variance for this one? Let me go to the next slide because there isn't any space left. What happens to the variance of this expectation of my E test? Well, let's look at it. Variance of 1 over k, summation k is from 1 up to k, and then E of k. This is small k. Okay, I've already created a lot of confusion, but let me write it as a small k, right? Okay, so now this is a scalar multiple if you think about it, this like 1 over k. So we can rearrange terms and like bring this out because this is a scalar multiple. This goes out and we have this equal to the variance of summation k is from 1 up to k and this thing. Okay, now we know that the data points are IID, as I said when we were calculating the expectation for my test error. And so similar to that, here E of k are all independent. Therefore, again, just like we did with the E test, expectation of E test, we can do the same here. And so the variance of E test is going to be 1 over k squared times k of variance of E of k, right? Which is nothing but 1 over k variance ek. Okay, so we have the variance, we have the expectation of the e-test, right? We have both of them. And so we can say that the test error is the estimate of out of sample error, or rather test error is the unbiased estimate of out of sample error, and it obviously has some variance in it, right? So basically we can come up with some heuristic statement if we think about it, which is somewhat like this, because we are after like E out. So we can say that E out is almost equal to E test, but now we have this variance, and so we can say with plus minus 1 over square root of k, square root of this variance ek for any point k. Okay, so this is all good. Now we got some way of representing our relationship between this E test and E out. And we know that there is some variance when we are doing the calculations. And this is all good. And in a perfect world, we do not, like, obviously all of this is good in a perfect world, but we do not have the ability to generate this test set, right? We've been talking about this test set because the big assumption here is that I have access to every data, everything that I want. So because I don't have the ability to generate this test set, what should we do? Or in other words, can we do something similar? Like, because this is all good. I mean, I got a very good unbiased estimate of my test error, right? And so basically I want something similar, and let's actually look at that in the next video.